Okay, so today we're going to talk about matrices, geometry, and inverses. One of the main goals of today is to connect different types of matrices. These will indicate transformations from R2 to R2 to different types of geometric transformations that you're familiar with. So rotations, we have stretches, reflections, and a couple maybe that we haven't seen yet. So shears and projections. And I want to just create a zoo of all these different types of matrices so that you can see that these transformations, when we write a box of numbers, they're actually geometric in nature. And then toward the end, we're actually going to try to combine them and see what that does to matrices. So let's go ahead and just create this zoo. So we're just going to go one by one. The main thing that we're going to use when we do this to create these matrices is the idea that the matrix that corresponds to a transformation is simply a concatenation of what happens to all the standard basis vectors. So in the notes, I typically write this as E1 because otherwise it looks really long and boring, and this would be E2. So this is E2 and this is E1. And all we have to do is figure out what happens to these basis vectors. Since we're going from R2 to R2, we only have two standard basis vectors. If we went from R3 to something, there would be three standard basis vectors and so on. And so for each of these types of transformations, all we need to do is figure out, okay, if I start with one of the standard basis vectors, where does that end up? So in this case, we're going to rotate by theta. So we're going to rotate by some angle theta. And that's just going to end up somewhere else. And likewise, we're going to start with our vector 0, 1. We're going to rotate that one by the same theta. And that's also going to end up somewhere else. And so the question is, as a function of theta, where does that end up? So one thing that's really nice about trigonometry is that if you always measure theta, the angle that you're interested in, then the result on the unit circle, that point right there that's on the unit circle, is going to be just cosine theta, sine theta. So that means that if we rotate the standard basis vector 1, 0, that's on the positive x-axis, and when you measure from the positive x-axis to another point on the unit circle, that end position is always going to be cosine theta for x and sine theta for y. And just for emphasis, I know this is one of the corniest things that I say, but this comes in alphabetical order, and this is in alphabetical order. So if you ever have to remember how the unit circle translates to cosines and sines and r's and thetas, just know that cosine and sine are in alphabetical order, and x and y are in alphabetical order. Okay, so what about this other vector? So this other vector here we first have pi over 2 plus theta. So that means that the total angle going here is measured. This is not just theta, but this is going to be theta plus pi over 2. So altogether, this point is going to be cosine of theta plus pi over 2 and sine of theta pi over 2. So now we can just write our matrix. Our matrix is just, for the first entry, is going to be cosine theta, sine theta. And for the second one, we get cosine theta plus pi over 2. And make sure you put those in parentheses, and sine theta plus pi over 2. And so that's a matrix. Okay, so you should probably be screaming and hollering because I said that linear transformations only have x's and y's in them, and they don't have cosines, sines, ln's, square roots, or squares, or plus b's. They don't have any of these, and here I am, there's a matrix where we have cosines and sines. But the key thing is what this matrix really says is that these are the coefficients of the transformation. This says that the rotation of theta of a vector xy is equal to cosine theta x. So this cosine theta comes directly just from the matrix. That's the coefficient of x. X itself, there's nothing special happening with. You predetermine theta. You say, I want to rotate 45 degrees. I want to rotate 75 degrees. And then that fixes theta, which fixes cosine. Cosine, once you pick your theta, cosine theta is just some number. And likewise, this would be cosine of theta plus pi over 2 y. Sine, sorry. Oh, no, it's cosine. That's right, cosine. And sine theta x plus cosine theta plus pi over 2 y. So the coefficients themselves are cosine sines, but the x's and y's are not. So that's okay. Okay, another thing I should mention is that there's a way to simplify this, is that it turns out that we have cosine and sine are just shifts of one another. So if you add pi over 2 to theta or 90 degrees to theta, and you take cosine, that's the same thing as sine. That's just taking the sine wave and shifting it. So this part right here is just sine. Sorry, that's minus sine. And we have sine, and this one turns into, oh, sorry, this should be a cosine. Sorry, that should be a sine rather. And this turns into a cosine. So sine of theta plus pi over 2 is actually cosine. All right, so every rotation matrix is going to look like this, which is pretty cool because it's not something you'd expect. You'd expect a rotation to actually be more complicated, but every rotation is just multiplying by a matrix. So what's something else we can do with matrices? We can do stretches. This one I don't want to spend too much time on because this is mostly self-explanatory. We're going to take the 0, 1 vector and we're going to stretch it by a factor of k. So we stretch this by a factor of k. Then what do we get? We end up with k0. So that means our first matrix, the first column in our matrix is going to be k0. And if we stretch the other standard vector, 0, 1, by a factor of L, then this is going to be 0L. And so you end up with this nice diagonal matrix. So this diagonal matrix is a matrix that only has entries in the diagonal and 0 otherwise, is going to encode these stretches. Now it also does contractions because there's nothing actually special about K or L being big. K and L can be small. So if K and L are small, it turns out that you get a contraction. These vectors just contract. So you take the same standard vectors. What's going to happen here is you get on the right, they're just going to contract. They're going to get smaller, but this is just times K. If K is small, right, and L may be a little bigger than K, but those are smaller. Now this is a contraction and it uses the same diagonal matrix. And even then, we can do reflections. If K or L are in fact negative, you get a reflection. So let's say you want to reflect both of these vectors. If you want to reflect both of these vectors, so a true reflection is you have K or L equal to 1. So I want to emphasize K or L. So in one case, you reflect over the x-axis and the other one y, but if you do both at the same time, you just get something that looks like this. Right? It turns out that if you reflect both of them, it's not a coincidence you get a rotation. So do a double reflection is the same thing as a complete 180 or pi radian rotation, but you may only reflect one of them. So you can do combinations of these. So you might only reflect one. So if you reflect only one, for example, if we want to reflect over the y-axis, we're going to reflect over this axis right here. That means we're going to reflect. That means that that standard vector is going to reflect. So in this case, you get minus 1, 0. But the green vector, the other standard vector, isn't going to reflect at all over that. So it doesn't change. And so it's going to be 0, 1. So you can reflect one or both. But if you reflect both, that's akin to a rotation. So that's kind of interesting about these matrices. So the main idea here is a diagonal matrix corresponds to a stretch if it's a big number, contraction if it's a small number, or reflection if it's negative. Those ones are a little intuitive. Let's start doing some less intuitive ones. So you might have a shear. So a shear is kind of like you have a box. So let's pretend you have a box. And you're gonna kind of, move it to the side without changing the height at all. Right, so you might end up with that one. And when you move it to the side without changing the height, but the walls of the box, the sides of the box are gonna shear to the right as well. So what's gonna happen is you're gonna end up with something that looks like this. And to make that transformation happen, one of the vectors is gonna change, but the other one's not. And so we might say that this is a shear where you go from 0, 1 to K1. So that very simply gives us that first vector in the matrix. And then this one's going to remain the same. And what's important about this particular transformation is all the other ones up till now has preserved the orthogonality or the perpendicular nature of the standard vectors in both the before and the after. But when you shear something, the standard bases may no longer actually be perpendicular in the after picture. So a lot of transformations have some sort of shearing going on into them, and this is how you get it. And you can shear in the other direction, of course, right? So you can shear the box up and down instead of left and right. So perhaps you might push the box against the wall right there. You might end up with a picture that looks like this. So that's the after picture. Let's make that the after picture. So this would be 1K, and the other one remains the same, 0, 1. So this is a different type of shearing, just up and down instead of left and right.